I'm live now. Hello, everyone. Thanks for joining. I know there are many interested sessions happening at the same time, particularly Venkat and Josh Long. So that one is good. I'm sad that I missed it, but yeah. Thank you for joining in this session where we're going to talk about profiling and specifically continuous profiling. What continuous profiling is, why do we need it, how it differentiates from traditional profiling or profiling as we know it, and why it's important to add it in your observability stack, and obviously what costs it's come with, just to have an understanding if do we need it, when, and how much it would cost. Before that, quick intro, the boring part. I'm Mohammed. I work for a small audio streaming company called Spotify, and I'm also Google developer expert for Google Cloud. And who has been on call before or got paged during the night? Exactly. So you know that feeling of waking up in the middle of the night. This is, by the way, generated by DALL-E. And a lot of the pictures that I'm going to use, they are generated by ChatGPT image generation, which is, or OpenAI image generator, DALL-E. And you will see a lot of spelling mistakes. That's not me. That's just the AI failing to understand simple English. But yeah, the idea is being on call is hard, and what adds to that is when we face a lot of challenges and lack a lot of tools that enable us to proactively or reactively in case of incidents, but proactively before that, trying to limit the amount of when we need to page the on-call people. But I've been on call and I've been waked a lot of times, and this is exactly how I look. So it's the picture is spot on. But why do we need on-call, and why observability become more and more important? A quick look back into history, we can see that in the 90s, this is how the majority of application looks like. It was a simple flow of communications between the client and the server. When the request came in from the user, it passes the browser, goes to the server. There's probably a shared or a single database in there, which was single unity of deployment. All the components are tightly packaged together into a single unit of deployment that is deployed. The problem with that we figured is when we want to scale, this is going to probably hit hard. So in order to scale, we started to break that monolith down into multiple services. And we started by what we call service-oriented applications, or SOA, and we needed to, the idea was basically to split the monolith down into multiple services, and those services collaborated together in order to achieve some means, either by passing simple data or achieving some functionality or some feature. But we needed some sort of interconnection, and for that we used ESBs and MQs. But even with that, we still have, so the organizational, if you ever worked with ESBs and SOA, you know, the promise was big, the implementation was hard, especially from an organizational point of view. So we ended up facing more organizational challenges than what we needed to do. So in order to scale even more, we started to break the monolith down smaller. And in 2010, we introduced microservices. And here we move it toward dump pipes, basically using REST, gRPC, whatever, to pass simple data, and we use it to eBPF contract to pass the data between multiple services, and it just exploded the number of services that we need in order to build our applications. However, distributed systems follows Murphy's law, which says that anything that can go wrong will eventually go wrong. And that is true, especially when you have multiple instances of your services running for your applications. Distributed systems added a lot of complexity, especially added a lot of challenges in terms of observability, in terms of execution, in terms of the mental model and how we see our applications. So it's become more and more challenging to monitor and react to those applications. Services no longer start and stop in the same time at a predictable manner. Just restarting your application no longer works. So there are things that the monolithic architecture guaranteed that are no longer true when we move it to distributed systems, and especially microservices. Some of those challenges are, as I said, monitoring, part of it like observing the interaction between those services. Microservices and service-oriented architecture in general and distributed system involve passing data between multiple instances of your service and services. So observing the interaction between those services becomes really, really hard. Traffic management, doing things like A/B testing, canary deployment, and everything that goes into traffic management and how to distribute traffic and tune where to go what goes where, basically, becomes even more challenging when we move it to distributed systems. And that can introduce some inconsistencies and consistencies within your application. Securing the communication. If you remember, as I mentioned in the beginning, there was a simple flow of communication. Now we have multiple instances. So the overhead of adding security, be it encrypting traffic, become more and more tricky. How are you going to encrypt that traffic, especially that you have multiple instances of your services and multiple services running. And finally, managing timeouts and communication failures. If you have ever run distributed systems, microservices, in instance, you know that network is not resilient. Failures happen. And how to build that resilience application, how you can avoid such thing like cascading failure to when a server is having a hard time, not to break your whole application, how to build that resiliency, how you can fine-tune your application to be more resilient in face of timeouts and communication failures. So just to say that distributed systems is hard, and we probably already know that. And in the domain of risk management, we use Johari framework or Johari window. And it's a simple framework that distributes the risks into 4 categories. I'm used only 3 here, but there are 4. There are the known nodes, known unknowns, unknown knowns, and unknown unknowns. And we're going to limit ourselves to just the 3 that I'm mentioning here. So the first one is the open area, which is known knowns, the things that we know about our application. And those are what we call trivias. We know that if you divide something by 0, it's going to arithmetic exception. If you're going to call a method or an object or a field on a null object, it's going to throw a null pointer exception. So there are trivias that we know, and we know how it's going to react and know how application is going to behave when something happens. So that's the open area, and that's the known knowns that everyone within the team, within the org, basically knows. And there are the known unknowns, the things that we know, but still surprise us when they happen. For example, we know that a memory leak will basically bring our application down. So we do a lot of things in order to avoid that memory leak, but when it still happen, it will eventually happen. And when it happens, you need to track it down. And you know that, for example, when your container will have, when your out of memory exception. So basically means that you reach the limit that the container or the container daemon basically clear application because you consumed all the memory allowed to it. So you know that you have a leak and you know how it reacts, but you're still missing what's causing that. So that's basically a known unknowns. And then the last thing is the unknown unknowns. And those are the things that we don't know how our application is doing. And those what causes basically outages. For example, a small dependency that you are adding to application that behind the scenes calls another service, a third-party library, and uses an authentication. You're using it 99% of the time, it's fine, nothing happens. But the one time when that third-party auth service goes down, your whole application basically breaks because that's an important piece of your application. And you inherited it as a dependency, and so that third-party dependency or third-party auth service becomes a hard requirement for your application. And then when that third party goes down, your whole application goes down. So basically, what we are trying to do in distributed systems when we're monitoring our application is to try to uncover the known unknowns and help to proactively debug the unknown unknowns. And when you hear about chaos engineering, basically, this whole discipline is trying to minimize what we call the unknown unknowns. We are trying to break production in purpose in order to discover how our application will behave in the face of network outages, cluster outages, database outages. So basically, the whole chaos engineering discipline and practices are basically to limit the amount of unknown unknowns when they actually happen. And we have been using a lot of tools. Basically, 3 of them can be categorized within 3 categories, which we call pillars of observability. I'm aware of the spelling mistakes here, and as I mentioned before, those images are generated by DALI. So I tried to correct them, but my editing skills are not that good. It ended up worse than this one, so I took the risk to keep the spelling mistakes and use the image as good as it's. But back to the presentation. So we have 3 pillars of observability, or at least that's how we called it. We have logs, metrics, and traces. Logs are basically textual information that we print, and they give a lot of context about what happens and why it basically happened. They are pretty easy to operate. They are pretty easy to implement. When you have an issue, you basically try to debug it, and if you need additional data, you go to your application, add a single line of logs, and try to understand why your application behaving the way it is. They are relatively cheap to operate. They add a lot of context when they're actually. Sorry. So we use them a lot to troubleshoot, understand the why rather than what actually happens, and they help us to debug and understand how our system is behaving and why it behaved the way it did. So that was the first one. The second one are metrics, which are numeric values that gives an overview of the health of your system and the performance of your system. So we basically log them, collect them, analyze them, and represent them in a way. Could be in a different graphs. And KPIs in here could be CPU usage, memory usage, latency, you name it. And it helps us to understand in real time the health of our system. If there's a memory issue, we can see an upward trend, and we can see when there's an out of memory kill or something, why it actually happened, because we reached a certain level. If you want to implement, or if you have auto scaling and your basically instances went up, you see that if you basically have a rule around CPU consumption, you see that why it went there and why the instance actually started. So basically, it gives the health of the system, and we can track the application in real time in them. And then we have traces, and traces appeared in the face of distributed systems, basically trying to track the journey and the life cycle of our application from the moment it left the user client until it went back to it. So it helps us to understand the full picture, what services has been called, what contribute to the error, the latency, and it helps us to track mainly bottlenecks within our application. So you have the full journey of your application. You can understand why this request is getting slow. You can track it down and find which service or services are actually most contributing to the latency of your application. And it helps us to also, if there is a faulty error, it helps us to understand where the error actually appeared and help us to debug and track where the error originated from. However, I was super proud of my picture that was generated by DALI, and then I published it in Twitter. And then Jonathan, who works at Pivotal, VMware, now it's called somewhere else, something else, but he's one of the guys working in Spring and Micrometer specifically. And he said, observability shouldn't be defined with pillars. And the amount of pillars doesn't matter. They can never show the whole picture, which is true. It basically means that we need to cross all the metrics and all the information that the 3 pillars of observability gives us in order to understand what's happening in our application and understand the whole picture. Each one separately would definitely give us a tunnel view, a scoped view of what's happening, and we will be missing the big picture in that case. And even with the 3 pillars of observability combined, we're still missing an important piece, or doing things proactively, understanding what is contributing the most into consuming our memory, what is consuming the most our CPU, why this latency is going up. So with the logs, we can understand the known nodes. If something happened, we can see the throw exception logged, we can understand why it was triggered, and then correct it. With the combination of metrics, logs, and traces, hopefully we can understand known unknowns. We know that a fault happened, an error triggered, and then we can go back, combine the 3, and find out the root cause. Known unknowns requires a different practice and different technique, and that's why profiling can help with that. It basically helps us to proactively track the health of our system. Things that are not provided in the 3 pillars of observability, as we call them. What method in my code is consuming the most CPU? What function is consuming the most memory? What's going into my thread? Why it didn't end up the way it should end? So it can help us proactively diagnose our application and hopefully proactively avoid incidents and optimize our code and application in order to improve it. And the example that I like to give is the 3 pillars of observability is similar to the vital signs, like measuring the vital signs, like the temperature, blood pressure, heartbeat, and all of that. So it gives you an overview of how the human body is behaving, if it's sick or not. You can check the temperature and see if a person is sick or not. But you need deep analysis, something like the X-ray, for example, to understand how the body is reacting. Is there why the body is raising its temperature? And profiling can be similarly thought of as the X-ray of analyzing our application and going deep into understanding why it's actually behaving the way it is, and proactively detect faults and issues. And there are different information or examples that we can use for profiling, or different types. So we have CPU profiling, and that is specifically when we are interested in what is consuming the most in my CPU. That as simple as that. We are interested in a specific moment, what my CPU is executing, trying that information and collecting that information. We can see how long a method is consuming in CPU, and in the execution timeline of my application, what is eating the most of my CPU. Wall clock is interested in why my function, why my method, why this call is taking long, be it in CPU or not, be it I/O, be it memory, anything. Allocation profiling is specifically targeting memory. What is eating? What's the pressure in memory coming from, and from what, and why? Log thread stop the word profiling is very similar to the wall clock, but it adds context to it. It adds thread information, especially if you have multi-thread application. A wall clock becomes a little less useful because we are missing the profiling information and the execution of different multi-thread applications. So basically, also interested on why my thread took so long to execute, but we're adding into that contextual information to understand better, especially in the case of multi-thread application. And heap profiling is basically interested in heap size, what goes into my heap, and it helps a lot in case of we're having memory leak that goes into the heap, and it helps to prevent things like going out of memory. And up until recently, we were using what we call traditional profiling. Traditional profiler, they have basically one big limitation, which is like they were resource intensive, meaning that we would need to operate them pre-production because how beefy they were. So basically, we need to install something on pre-production environment, testing environment, developer laptops probably, to debug and analyze and profile our applications. And that was a big limitation for the traditional profiling. And because of that, it provided limited visibility because all the fun basically happens in production. And Josh Long, pretty much in his talk says, which is the Spring Developer Advocate, he says like production is the happiest place on earth because like that's the place that your clients, your customers goes to in order to get value from your application. That's where we as developers ship our applications and meet our customers and clients, and basically where all the fun happens. However, traditional profiling didn't go to production because they were heavy to operate, and they were added a lot of overhead, and that overhead wasn't production friendly. So the majority of industry decided to not operate profiling in production and limit them into pre-production, which means that if something happens in production, you have limited visibility over why. And if an issue is happening only in production, which is 99% of the cases, then you are in the blind basically because how hard they were to operate. And then recently we started to hear about continuous profiling. And by recently, I mean 2000-ish. So it's not a good new technique, it's an old one, and it basically adds the continuous dynamic to your application. So we're continuously gathering data, gathering profiling information. So the first piece of it is continuously gathering that information and then dumping it somewhere. So there is a storage aspect of it. We store it generally short-lived. They need to be long-lived somewhere or compressed in order to optimize the storage for it when it goes to final storage. And then we need to visualize them. And that visualization is the final aspect of continuous profiling. So we collect the data in a continuous manner, we store it somewhere, and then we need to optimize the context because we are continuously gathering that data so it can be big. And then we need a way to visualize the data, and it needs to be low overhead. And the low overhead is the key aspect here. So mostly the promise is anything that is less than 2% overhead is acceptable. It depends on your organization, but all the profiling tools that I'm going to show today, the promise is they are add less than 2% overhead to your production application, which is generally acceptable compared to traditional profiling tools. And the first one to use continuous profiling term were Google. They introduced the paper in 2010, so we can assume that it was already in production for years before that. And they basically led the way, and so that's a valid QR code, by the way. You can scan it if you want to go to the paper. So they led the way and defined how the architecture of continuous profile, even today, looks like. And as I described before, there is the profile information, how to design a low overhead profile, and how to collect the data, where to store it, short-term and long-term, how to optimize it, and then where to save it, and analyze it and view it. So they released the paper, they released an open source project with it, and then it just exploded in popularity. So Google introduced the paper, Facebook, Netflix, and the big ones followed afterwards. And then the cloud providers, because we live in a cloud era, said, yeah, why not? It can be used for getting more money for the users and providing it as a service. So introduced in their profiles, and then a lot of open source projects appeared. I'm going to mention Pixie, Periscope, and another ones in the beginning and later. But then basically there is a lot of options available since 2019. It, I kind of talked about this, but to all the architecture, be it open source or not, follow kind of similar architecture. So we need a way to collect the data and collect the profiling information. And there are two ways to do that. Either have an agent that is running, that is agnostically collecting the information, but to write an agent needs to do a lot of effort there in order to keep it within a minimum overhead. Or there is the instrumented way, which means that you add code to your application in order to collect the profiling information that you are interested in and send those data to be analyzed afterwards. So once you collected those data, depending on the way you prefer, you send them for ingestion. Because we're collecting a lot of information, we want to analyze those information, clean them up, and then compress them if needed. And then the profiles is the heart of the continuous profiling thing. That's where all the logic and the magic actually happens. And we need symbols, and symbols are basically, you can think of it as the contact list in your phone. If someone sent you an SMS and you only have the numbers or the phone number, you can't figure who that person is. You always send back new number, who's that, right? So symbols are the contact list of what is getting executed in your CPU. The machine doesn't need to know what's the method name or what's the function name. But we do when we get the profile information back. So basically, it's one-to-one mapping on what is executed into what function maps to, basically. So it's basically, we call symbol, it's what's executed, and the reference of the method in a human-readable format to what's executed into the CPU or the thread or whatever. And then we need a way to store that information. We can kind of have a in-memory limited storage that to speed things up, but then a way to send it to a permanent long-term storage. So there are some implementation that is split it into two ways. Things that happen within a certain amount of hours up into a day can be lived within in-memory, and then for more long-term storage, we send it to a proper data storage. And then we need a way to visualize this. So we have a front-end application that basically shows the data that we sent in a nice way. This is basically the same thing. We collect the data, analyze it, and then visualize it. So that's basically the 3 big blocks that are common between all the continuous profiling implementations. How we collect, how we do profiling, basically what are types of profiling. So we have sampling profiling, which is a simple one. It's basically, we collect information at a certain amount of time, be it 10 milliseconds, 100 milliseconds, you name it. There is a simple and the most obvious one, and the one that was used for many years. So we collect the information and we analyze what is executed in my CPU. And then we collect all that information, condense it, and combine it back, and then we'll have a full an overview of what was executed in my CPU. So it's basically sampling, executing the profiler, getting the information we need X amount of time. We don't want it to be so close so we can overhead the CPU, and we don't want it to be so big so we get a limited overview. Generally, it's between 10 and 100 milliseconds. Event-based profilers, and that's when we are particularly interested in some events, like caching, database, some sort of event that happened, and we want to profile that event and how it actually behaved. And semantic profilers is when you add specific logic to your code in order to collect those informations. So it requires that you change your code in order to collect the data. Like, say, for example, you are particularly interested in executing executing a method that they call to database, and you want to profile that specific method. So you add profiling information or specific code that measure that and send it to your profiling tool. So basically, you are in control there and collecting information based on specific part of the code that you're interested in. And then thresholding profilers. And basically, here we are concerned and interested in the outliers. For example, if you are not interested in all the outgoing connections to your database, you're only interested in the queries that take more than 100 milliseconds. Let's say 500 milliseconds, half a second. So you want to profile the queries that take more than that, or specific events. So you have a threshold, specific threshold, or IO calls that take more than a certain amount of time. So you are interested in specific threshold defined in your application, and you want to collect information and profiling information about those events when it passes a certain threshold. I hope that was clear. Challenges. When we talk about profiling, those are generally challenges in all the tools, but with different levels. Symbolization is going to be always a challenge because to have the mapping, you need to store it somewhere. And the more storage you have, the more impact you can have on your profiler. So majority have a lot of techniques in order to overcome the symbolization and get better into it. But you may or may not run into symbolization issue, which is, again, mapping what is executed to a human-readable format. Efficient data collection. The continuous aspect of the continuous profiling is continuously connecting data. And we end up with a lot of amount of data. Having an effective algorithm for compressing, condensing the data, effectively storing it, either in memory, in local, or sending it to your data storage, it's important because we are collecting a lot of data. Expressive queries. We are humans, and we don't want to learn learn code machine, basically. We want a DSL language on top of our tool that enable us to basically collect the data. Let's say, for example, you're interested of all the methods that took more than 1 second to execute. You want to express that as fluent as possible, as close to natural language as possible. So expressive queries and some of the tools can be challenging. Correlation with other signals. Back again, to have the full picture, we would love to have profiling with the 3 pillars of observability, to have the 4 pillars of observability, as we call it now. Widespread adoption. This is less true nowadays as continuous profiling gain a lot of attention, a lot of momentum. We saw a lot of tools in cloud, open source, and commercial. So continuous profiling is gaining a lot of momentum. And ensuring accuracy and representative sampling, especially when we have the sampling profiling, how to tweak that number to have a real-world view rather than a distorted and faked view. Why we are, or you would be interested in continuous profiling? The first promise is cost saving. So when you start our application, basically we're in the one right there. For you is like the far left. Your application it needed a certain amount of resources. Your application grown, your users grown, business is doing good, but the amount of resources you need to run your application exponentially scaled as well. So you are paying bills in terms of either managing that infrastructure or to your cloud provider to manage it for you. And the resources needs your application to run grows as well. The promise with continuous profiling is it helps you to optimize your code. Like if you understand why your application needs so much memory, where you can optimize even in code level, going up to the code level, because continuous profiling, you can have user space code that you can understand, and also kernel space code. So you have the full view, basically. So you can optimize those code both in CPU and memory and other things, and basically reduce the amount of resources needed to run your application. So basically, that would be a saving that you would have while using profiling. So that's one of the promises of using continuous profiling. Also, better feedback loop. When you have continuous profiling, basically you deploy your application and then have tools that can analyze today's behavior compared to yesterday's behavior. Or how was the application behaving in this version compared to this version in terms of CPU consumption, memory consumption, latency as well. So you have this different view that you can compare application and track where you basically added a regression. So let's say your customer started to report that there was a regression happening. Your SLO in latency increased from 800 milliseconds to 1 second. Where this 200 milliseconds came from, probably introduced a regression. So you can go back to your continuous profiling tool, try to understand what bits in your code contributed to that 200 milliseconds meticulously, and trying to find and optimize it back as well. So basically, we introduce continuous profiling as part of our development or deployment journey. So every now and then, even daily, you can come and check and compare today's versus yesterday, or even deployments, and check what changed. Are things getting better or basically getting worse? And hopefully that would contribute to more proactive troubleshooting. You don't need your customers, your users to report things to you. When it becomes part of your day-to-day activities, you can go back and check and notice that you introduced an regression in the last deployment or so. And by proactively troubleshooting and fixing bugs, that would hopefully reduce the downtime for errors that could happen, and resource consumption going over the CPU limit or going over the memory limit, and even optimize your code to use less and less memory, or be tweaked in order to use the right amount of resources it needs. Latency, we spoke about that, and performance regression in general. When you deploy something, you can see after a few the impact of that code change, and if it impacted the CPU consumption, latency, memory, and so on. Acquiring profiles, I mentioned this before, there are language specific, so instrumentation, and there are agents. And we'll talk about one aspect of the agent in a minute, but then to acquire a profile, if you are language specific, we can use tools. For Java, for example, we have JDK Flight Recorder and Async Profiler. Go use pprof, which is the tool that Google open sourced as part of the paper. Rust folks have our AirB Spy, and Python has cProfile, and then other languages have different tools for it. But I wanted to talk briefly about the concept called SafePoint. So in Java specifically, because we have the JVM, it needs to perform a lot of options, right? Part of that options is the garbage collection. The SafePoint is basically a checkpoint where the JVM, in order to perform its function, it needs to make sure that all the paths that are executed within your code reach basically a SafePoint. So it can say that, oh, I can perform my function. For example, if the JVM is doing garbage collection, you don't want the JVM to prematurely removing some objects that are actually in use. So the JVM needs to reach that SafePoint. SafePoint is good to ensure that the JVM has the ability and the assurance and the confidence to perform the things it needs to perform. However, that concept introduced what we call the SafePoint bias when we talk about profiling. So the green is when we are collecting sampling information or profiling information. It's basically sampling. So the first one we're calling the new car method, and then the second one we're collecting the get method from the repo. Third one we're calling save. So that save is a little bit long, so it hits to samplings, and so on and so forth. The sampling bias is basically the JVM giving you information right when it arrived to the save point. So you are having basically this distorted view, this fake view that you're actually getting the information from the save point or when it was executed until it reaches the save point rather than when it was actually executed. And there is fine in the left part of the example, but here, imagine if something happens here, then we won't get it until it reaches the save point. So that's what we call the save point bias, basically, which is an optimization or a requirement within the JVM, but a lot of profilers suffered from it. GDK flight recorder, async profiler don't suffer from the save point bias, but if you're using other things, you need to be aware of it, basically. It gets even worse with the inlining. So the compiler, JIT compiler does a lot of optimization. So it collapses your code, basically, to speed up the execution of your code. So now your 3 aligned sampling information are all gone. You're basically getting the do something. And in your profiling, your nice graph that you will get in the end, you will hit that do something is taking X amount of time, while in fact, it was distributed between 3 other different methods. So that's basically a short introduction to the save point bias. If you are using profiling, that's something you probably need to be aware of it, especially if you're using Java and or a JVM language. Another way to acquire profiling, it's a new one, it's eBPF. So eBPF, very briefly, it needs a session on its own, but eBPF is a new thing from the Linux community in order to make the kernel, the Linux kernel specifically, programmable. And it does that by introducing a new couple of components. So we introduced some libraries basically to write eBPF program. eBPF programs have 2 parts: the kernel space code and the user space code. So the kernel space is the one that we are interested in. You write a kernel space program as using a library as any programming languages. You can use basically 2 languages, Rust and C, because they are the ones supported in the kernel. However, you can use Go and only Go, but Go basically compiles the code natively into C behind the scenes. There are some libraries that you can write in Go and compile it. But at the end, the code that is generated here in the bytecode is basically C compiled. They use behind the scenes a compiler that generates a bytecode, similar to what we have in Java, but this one is for Linux kernel. So we generate a bytecode, and then we load the bytecode into the Linux kernel. Before it gets loaded, it passes through the verifier, and that's a very important piece in the eBPF ecosystem, or eBPF libraries. So the verifier verifies that your code is actually safe to run. You need to verify that all your objects that you are calling have a safe pointer, and you need to make sure that this pointer actually exists. The verifier makes sure that all the paths that are executed in your method reaches as an endpoint. So you don't have a method, like you can't have a while true in an eBPF program. That's not allowed. You need all the execution paths in your program to reach a stable end in the end of your program. So if you code eBPF, verifier is going to be a nightmare. But if you pass the verifier, the code is JIT compiled into native code and then loaded to the Linux kernel. Or not loaded, but actually attached. So you attach an eBPF program to an attachment point. And those attachment points can be basically anything, because the Linux kernel has access to anything. Can be system calls, can be sockets, can be file systems, can be TCP/IP sockets. You can offload even some of the functionalities, especially in the network, to the hardware, if the hardware has eBPF support. So it gets treated even before it reaches the kernel. So that's an amazing functionality in Linux that has been added, and it's gaining a lot of momentum recently, and you probably already heard of it. If not, check eBPF, it's really cool. So yeah, and then I mentioned attachment point, and then when it gets attached, your program is basically invoked. So eBPF are event-driven. Think of these as events. So when, for example, there is an I/O event happening or a socket event. So a network packet came in TCP/IP. Kernel gets it and delegate the execution to an eBPF program. So it's basically it's an event-based framework or library, basically. So it gets invoked whenever there is an event that your program is actually listening to. And it's very fast because it's executed within the kernel. Oh, 5 minutes. Wow. OK, a lost count of time. Open source stuff. So for eBPF, continuous profiling tools, we have Pixie, Periscope, and Parka. I won't probably have the time to demo the 3 of them, but they're gaining a lot of popularity. I was planning a quick demo. So basically, a simple Java application. Can you see it? Maybe now it's really big. Simple Java applications where we have a region. And the region is defined in my Docker Compose. Yes. So we have 3 regions, US East, EU North, and App South. And the application is basically, if I go to my README, go up. So basically, I have a client load generator that sends requests to my 3 regions. It's basically a Docker Compose. And it's basically a ride-sharing app. It could be car, bike, scooter. So we have an order service. I have a controller that can call car, bike, or scooter, depending on what you want. I hope that's clear. And then I have an order service that basically handles the booking. And here I'm adding dynamically other tags. So I have region as a tag, and I have a vehicle as a tag. I'm using Periscope. If I go here, I need to go here. So Tags Explorer, I'm using Periscope. So basically, I'm tagging my application. So it's here. Push, is it clear for the people in the back? And then I'm interested in CPU. And then if I check the tags, OK, so that's good. I have a single view. If I refresh the application, OK, I need to last 30 minutes, for example. The application was running in the back. So just a Docker Compose, and the loader is sending traffic. And they have a lot of tags. Some of them are basically the region, my 3 regions, and my vehicle application. My vehicle, but should be 3 here. OK, let me refresh. You never know, demo effects. Oops. So select tag. No, I need to process, write app, CPU, and then it should here have vehicle, 3 of them. So we have table view and flame graph, and here the flame graph. So what I want to demo is basically the function here is taking a lot for bike. You can see that the CPU here consumption lowers when there is a bike compared to car. When I execute the car, the CPU consumption goes up, and similar to, what was the other one? Scooter, right? And it goes up, but not as much. So it shows me kind of there is an issue with the booking of my car vehicle. And then I can go even further and try to understand if there is a region-specific issue. So we can see for the car even, there is no issue, or relatively less issue in the App South. What was the other one? EU North? Is that the other one? EU. OK. EU North, that's the one. You see that it goes up again. And in the 3rd region, believe me, it's going to be as the previous one. So there is a problem in the car and a problem in EU North. Periscope and all of them have this comparison view where you can basically select the portion that you want to select, that you want to debug and understand. And here we're comparing things in the car that are EU North and non-EU North. And if we go down, we can see, for example, that, no, they are the same. No, there's something wrong in here. Execute. It did? It did, yes. So we can see here that order service is taking 23 minutes here. However, here is taking only 9 minutes. And then if we go down, we can see that There is a check driver availability that's taken most, and then mutex lock is taking 20 minutes more of that time. So if we can go to the diff view, hopefully, if you go to flame graphs, execute here as well, you can see a comparison that check driver is 90% of the latency. It's small here, sorry for the people in the back. 90% of the latency is basically coming from the check drivability. And then if I go here, it's basically, that's my method, and I'm adding, there is a big if here, if a region is EU North, then execute mute locks, and mute locks is basically adding that latency. So it's like a very damp demo to show that you can basically track latency down to specific tags. Time's up. Okay, final words. Sorry for deboarding. So Parka, I demoed Periscope, but Parka is kind of the same. Pixie is kind of my favorite. It does more than continuous profiling. It has also observability and monitoring within it as well. So looking ahead, eBPF as a unified collection method. I talked a lot about eBPF, but I believe it's kind of the future when it comes to CNCF or cloud-native stuff, especially in observability and monitoring. It's getting there. And then OpenTelemetry are starting an task or an issue to support continuous profiling. So soon it's going to be part of the OpenTelemetry. Thank you. I'm running out of time. And here are some links, especially the demo and other talks that can help you with that. Sorry for the delay.